Okay, hello everyone. Today we are going to learn first category set and second category set and baire category theorem. So first we will discuss about definition of first category set. What is first category set? Let's see. A subset, let's say a subset of a metric space of a metric space XD is said to be the first category set if it is union of countable family of nowhere dense set. Okay, so it means that a subset of any metric space said to be a first category set if that subset is a union of countable family of nowhere dense set. What is nowhere dense set? We know that nowhere dense set is like interior of any set is phi, means empty set, then A is said to be dense set. We know that if interior of any set, let's say any set contain only 2 point 1 and 2, so interior of this set, if it is empty, so then this would be nowhere dense set. So first category set it is that a union of all dense set, all nowhere dense set. So it is, let's say, nowhere dense set. So A equal would be union of n equals 1 to infinite, union of an, where an is nowhere dense set. Means if you take interior of an, that would be phi. So I hope you got it. Okay, let's see the second category. Let's see second category set. What is second category set? Second category set. It's very simple. If a subset of any metric space is not first category set, then it would be second category set. A subset A of metric space XD is not first category. It's not first category set, then it is said to be second category set. Means here interior of an would be 5. I hope you got this. What is first category set and then second category set? Okay, let's talk about baire category theorem. What is baire category theorem? Okay. Baire category theorem. What is the statement of baire category theorem? Any complete metric space is a set of second category. The set of second category means, like, if we take any complete metric space, let's say xt, so that would be the set of second category. So to prove this, we will take let's say x. Suppose we will go as opposite. Suppose, if possible, let's say x is a set of first category. If it is first category, then its interior, its subset interior does not contain any point. So if x is a first category, so x would be union of all nowhere dense set, right? An. Here An is nowhere dense set in X. Means interior of An equals to 5. So if X is a first category set, and A would be the subset of X, then if we take A1, A2, An, all are empty. All are empty. If there exists any open ball in them, right? So since if we take A1 is a nowhere dense set. Let's say A1 nowhere dense set. Then there exists an open ball, let's say B, with radius epsilon 1 and with center x1, and that does not contain any point. We know that interior of any set is empty. Means if that set contain any ball, So ball does not have any point of A1. Any point does not contain any point of A1. Similarly, if we take A2, A2 is nowhere dense set also. Then there exists an open ball, let's say BE2, which is not larger than B epsilon 1. If we take B epsilon 2 x2 ball, which is a subset of B half epsilon E1 epsilon 1, and that this ball also does not contain any point of A2, that does not contain any point, because its interior is empty, any point of A2. Similarly, if you take A3 is also nowhere dense set. Nowhere dense set. Then there exists an open ball B epsilon 3 x3, which is contained in B half epsilon 2 x2, that also does not contain any point of it. Point of A3. So overall, if we proceed this process at the nth term of ball, so if we proceed this process, then we can construct a ball at the last B epsilon n xn. Okay, so we can write here. So B epsilon n xn, which is consist in B epsilon n minus 1, half of epsilon n minus 1, and with center x n minus 1. Okay, and if you take B epsilon n and xn, if B epsilon n and xn intersect with an, then that would be phi, that would be empty, because an is a subset, but B epsilon xn is not having any point but a and a is having points. If we take any common, if you take any common between them, so that would be empty. And third one is epsilon n is less than half epsilon n minus 1 for all n equals to 1, 2, 3, so on. So here we see one thing here. Let's epsilon n, from the beginning. First we take epsilon 3 epsilon n less than half epsilon n minus 1, then 1 upon to the power 2 epsilon n minus 2. If we continue this at the last, we will have 1 upon to the power n minus 1 and epsilon n minus 1 minus n minus n plus 1, that would be 1 upon 2 n minus 1 and epsilon 1. So okay, by keeping this view, in this view, the fact will come: an open ball B epsilon n contains all subsequent balls, right? It's containing all balls. So keeping in view of the fact that open ball B epsilon n xn contains all subsequent balls, right? So if we take any integer, any positive integer, if we take any positive integer, let's say p, so we can say that xn, which is the center of B epsilon n, and distance between xn plus p and xn, that would be less than half of epsilon n. We know that that we take that metric space xt, that is complete metric space. So every Cauchy sequence in complete metric space converges any point, right? So here xn, let's say here xn is the sequence xn is a Cauchy sequence, right? And xt is complete metric space, right? So it will converge. So xn converges to x, right? And where x belongs to capital X. So we can write it like this. Limit n tends to infinite, xn equal x. X would be the limit point of the xn. So, and if we take this expression as a equation first, and letting p tends to infinite from equation first. So the equation would be like this: dx xn, which is less than half of epsilon n, and epsilon is less than epsilon n, we can say. So we can write dx comma xn, which is less than xn. So we can create a ball in which a point x, so bxn xn. Okay. So from this we can say that it is the ball, the subset x also contain x in it, right? A subset an also contain x, because the nth ball of an is containing x. So which is the contradiction, right? Because we took an, because we took an as a nowhere dense set, right? An is an nowhere dense set, and if we know that nowhere dense set means it does not contain any point, but at the last it's containing a point x, right? So which is contradiction. So we can say that interior of an does not belongs to phi, because it's containing x. So x would be, so union of an tends to n equals to 1 to n infinite equals to x will be second category set, because we know that if interior of any subset of any metric space does not belongs to phi, it is not phi, so then the set would be second category set, hence proof.